Here's a bit of commonly used experimental language, which we will get more familiar with as we go into our first example. People or rats or anyone who is participating in a study, these individuals are referred to as subjects, and the treatment is the condition that is applied to the subjects. A good study will often have a control group, which is no treatment. This is intended to be some form of no treatment at all, to measure the effect from a treatment group. And we would use a placebo, like a sugar pill, for example. This is the classic sugar pill. This is a treatment that's designed to have no effect. And the point of a placebo is so that people don't know whether they're in the control group or the treatment group. If the treatment group is taking a pill, you want the control group to take a pill also, so that they don't have too much of that psychological influence on their results. Blinding is often necessary also. The blinding is behind the idea of a placebo. A blind experiment is an experiment in which people don't know what treatment they're getting. So single blind, the participants themselves don't know what treatment they're getting. This would be the point of using a placebo. Double blind, the participants and the people interacting with the participants don't know what treatment they're getting. So for example, maybe the doctor who is prescribing a medication, after getting consent from the patient to participate in the study, the patient knows that they may be given the real drug and that they may be given a placebo. The doctor hands them something, records whether it was coded red or coded blue in a notebook, and the researchers know which is which, but the doctor doesn't. The point of a double-blind experiment is to make sure that that doctor doesn't exude some sort of bias, whether conscious or unconscious, onto the patient about whether they're getting the real treatment or not. You could especially imagine that a doctor who knows and cares about his or her patients would be inclined to want to give a little bit of extra advice if they knew that the patient was getting a placebo, right? Like you might, as a doctor, be more concerned about that person and tell them to do some other things to make up for it. So that's the point of a double-blind study. Even though we want to care about the participants, we also want to be able to get some meaningful results. Okay, so we have as an example this fairly famous aspirin study in the 1980s, in which 22,071 male physicians were recruited to try out the theory that aspirin might reduce the chance of a heart attack. So they were randomly assigned to take aspirin or to take the fake aspirin pill, and we found that the physicians who took the real aspirin had 44% fewer heart attacks than those taking the fake aspirin. So the subjects are the individuals in the study. This is the 22,071 male physicians. And the response variable is heart attacks. We're trying to measure the impact of aspirin on heart attacks. The treatments are the real aspirin and the fake aspirin. And together, these make up the explanatory variable. A placebo was used because instead of just telling them not to take anything, those in the control group were taking the fake aspirin. So we would say yes to this and reference that fake aspirin that we just mentioned above. That would be the placebo. The purpose of blinding here, the blinding was achieved by using a placebo. The purpose of blinding here is so that the participants don't know which drug they're taking. They don't know if they're taking the real aspirin, and that isn't going to then affect their behavior. In particular, we would be concerned about any behaviors related to the chance of a heart attack. For example, if you know that you're taking the aspirin each day, each time you take that pill, you think of it working its effect. Maybe that's going to make you more likely to indulge in good behaviors because you feel that you're doing something good for yourself. Maybe it's going to make you more likely to indulge in bad behaviors like eating more fatty foods, not exercising, that sort of thing, because you feel like the aspirin's kind of got it all covered, right? It can have effects in both directions, but knowing that you're taking a treatment having any effects at all in your behavior in ways that could influence the response variable is really serious for trying to trust the results of the study. So this is why we have blinding and why it's so important to use that placebo. Now, can we infer causation and can we generalize this result to the population of all adults? That's where we have to think back to the diagram we saw. We can infer causation if the explanatory variable was randomly assigned. We can generalize the result to the population if we're working with a random sample. So again, we refer to this diagram here. If the sample was randomly selected, we can generalize to the population. If the explanatory variable was randomly assigned, we can make conclusions about causality. We very rarely can successfully do both. So in this study, the explanatory variable was randomly assigned. It is part of the description that these male physicians were randomly assigned to take the real or the fake aspirin, so we can answer yes. We can infer causation. The explanatory variable, which is the two treatments, was randomly assigned. Can we generalize this result to the population of all adults? So the population is all adults. We know that the subjects in this experiment were all male physicians. So at best, our subjects are representative of all male physicians. We would only know that if we also knew that they were randomly selected or that maybe we had contacted all of them. This was a pretty large study. We definitely can't consider these male physicians to be representative of the population of all adults, and they definitely were not randomly selected from the population of all adults, so we would have to answer no to this. The subjects, the male physicians, were not randomly selected from the population of all adults. So remember, each time you see a question of this nature, can we infer causation? Can we generalize to some particular population? We want to picture that diagram. Causation only if the explanatory variable is randomly assigned, which is generally the case in a randomized experiment. Generalizing to the population only if we can truly consider our sample to be representative, and the best guarantee that it's representative is that it was selected at random.